Welcome to this explainer. Today, we're diving into what I can honestly say is a truly radical proposal in the world of mathematics. We're looking at a fascinating source paper that essentially asks us to do the unthinkable, completely replace the heavy ontological burden of infinity with a much more grounded concept, something called extreme magnitude. And the best part, it claims we can do all of this without breaking standard mathematical theory. It's a huge, bold claim, and we're going to unpack exactly how this works.
So, we're kicking things off with a massive question. Is infinity mathematically real, or is it just an illusion? We're asking this because our deeply ingrained historical habit of relying on infinity, well, it might actually be causing serious epistemological friction. Think about it for a second. We use infinity all the time in math, right? But is it an actual destination or just a handy placeholder for something we literally just can't reach? According to the source material, treating infinity as a tangible, real thing is starting to really weigh down the rigorous architecture of the formal sciences.
The author of the paper puts it pretty bluntly, stating that the linguistic reliance on infinity has transitioned from a useful heuristic to an ontological burden. Basically, for the senior mathematician, the actual word infinity remains fundamentally ill-defined. It forces us to lean on Cantorian abstractions, those nebulous traditional mathematical ideals of infinity, that actually end up obscuring the true nature of scale. The argument here isn't just academic pedantry. It points to a real structural weakness in mathematical logic.
Section 1. The problem with infinity.
Okay, so if infinity is a flawed operational concept, how exactly do we fix it? Well, the proposed solution is to recognize what the author calls hugeness or extreme magnitude. We're talking about magnitudes that are simply too big to be called numbers anymore. A proper number has specific properties, right? Identifiability, comparability, you can do arithmetic with it. This whole paradigm shift rests on recognizing that infinite size functionally just doesn't exist compared to numbers that are simply way beyond our capability to ever reach.
Section 2. Infinity versus extreme magnitude.
When you pit these two frameworks against each other, the core methodology gets brilliantly clear. On one hand, you've got Cantorian abstractions, which are ill-defined and carry these heavy, unprovable transfinitive burdens. And on the other, you have the finite paradigm, offering a totally grounded logic of scale. You see, in math, progress often relies on functional indistinguishability, meaning if two conceptual frameworks give you the exact same systemic results, you absolutely have to treat them as theoretically equivalent. Whether a value is truly transfinite or just incredibly huge, the operational impact on the math is exactly the same.
The really crucial takeaway here is that systematically reclassifying these concepts completely neutralizes that transfinite burden. For instance, when we shift our thinking from points at infinity to magnitudes that are too big to be numbers, we actually manage to stabilize projective geometry using finite thresholds. And if we shift from infinite sets to quantities beyond capability to reach, the result is that we completely eliminate Russell-type paradoxes, those weird logical loops where sets contain themselves, simply by capping set cardinality at reachable limits. We're grounding the theory in a reality that is vast, sure, but entirely conceptually coherent.
Section 3. Rethinking the Riemann hypothesis.
Now, to prove the math doesn't just completely break under this new paradigm, let's apply it to a famously unsolved problem, the Riemann hypothesis. Traditionally, this concerns the distribution of infinitely many primes, but under the finite paradigm, we actually rephrase it. It instead becomes a problem dealing with an enormous amount of primes, an amount so big they're too big to even be primes anymore, way beyond our capability to reach them. We're taking a conjecture that ostensibly deals with the transfinite and reformulating it entirely within the bounds of the unreachably vast.
Let's break down exactly how this logical boundary works. It's kind of like walking to the absolute edge of a map. Step 1, you assume an enormous amount of primes. Step 2, you cross that horizon of reachability. And then step 3, distinguishing between a prime and a composite number becomes completely untestable, which makes the very property of primality functionally irrelevant. It's this delightfully human philosophical paradox. Once a number gets so big it exceeds our capability to reach it, we can't test its properties anyway. So transitioning from prime to extreme magnitude isn't losing data, it's just finally acknowledging a logical boundary.
And through all of this, the validity of the hypothesis remains completely unshaken. Ultimately, since a counterexample hasn't been found within reachable numbers, and the logic totally holds up for all huge numbers, the distinction between forever and unreachably far is, well, it's a distinction without a mathematical difference. The results of the conjecture remain invariant whether you use infinity or extreme magnitude.
Section 4. A new finite paradigm. So what does this shift actually mean for professional discourse?
Let's take standard calculus as an example. We're all taught about limits approaching infinity, right? But under this new framework, we can entirely circumvent infinity as an epistemological placeholder. Instead, a limit is much more accurately described as a value approaching a massive threshold, a threshold that's too big to be called a number, but still exists entirely within the logical constraints of magnitude. It effectively forces mathematicians to confront that capability to reach head-on.
The benefits of adopting this finite paradigm are surprisingly rapid and profound. It gives us incredible precision of scale, letting us identify quantities as an enormous amount rather than just tossing them into some abstract void. It completely removes those ill-defined abstractions, which stabilizes both geometry and logic. And honestly, most importantly, by stripping away the mysticism of the infinite, we foster a much more honest, precise form of professional discourse. For anyone working with math, this could mean finally unlocking some incredible new insights into computational theory and the actual limits of numbers.
This brings us to a really powerful concluding thought from the source text. It says, by discarding the ghosts of the infinite, we do not diminish the horizon of mathematics, we finally acquire the courage to measure it. I love that. It beautifully reminds us that our reliance on infinity is really just a historical habit. Discarding it is an ontological imperative if we want long-term clarity. Our true future doesn't lie in chasing the unreachable infinite, but in the rigorous, grounded mapping of extreme magnitude.
So I'll leave you with this final thought. If we actually discard the ghosts of the infinite, what new horizons will we finally measure? Once we stop chasing this unreachable, kind of ill-defined concept, what staggering realities of our truly vast, yet entirely finite universe will we finally have the courage to discover? Thanks for joining me for this explainer, and keep questioning those horizons.